Good morning. Today we are going to see about the small signal analysis of a transistor. So we all know what is a transistor. So transistor is nothing but a semiconductor device and it consists of three terminals: base, emitter and collector. It is a current control device. So first we can see So we know it has three terminals, that is the first terminal is base and we have the emitter and we have collector. So it is a current control device and the voltage that we are supplying between the two terminals, for example base and the emitter, plays a major role in providing the output current through the another one terminal. For example, it is collector. So the collector current depends only on the voltage what we are supplying between the base and the emitter. So the VA characteristics for a transistor is non-linear because the voltage we are supplying between the base and the emitter will have an effect on the collector, so that the VA characteristics is non-linear for a transistor. Because of this non-linearity of the transistor, we are going to analyze the transistor using a small signal analysis. So in order to analyze a transistor as a small signal model, we are going to make a transistor as a two-port network. So first we can consider a transistor as a two-port network. So this side we will have the input voltage as Vi and this side we will have the output voltage as V0. The input current will be represented as Ii and the output current will be represented as I0. So this is a two-port network for a transistor. So automatically a question arises, why a two-port network has to be used? So in order for the simplified analysis, we are moving for a two-port network. So we are going to consider a input as one port and output as one port for the simplification of the analysis. So first we can have the inputs which is nothing but Ii and Vi. The outputs are nothing but I0 and V0. So what we are going to do is, we are going to find the equalization terms for this one. So it may be a H11, H12, H21 and H22 or Y11, Y12, Y21 and Y22. Otherwise it can be Z11, Z12, Z21 and Z22. So these four parameters we are going to analyze using this two-port network. So I have already told that we are going to analyze this three. As I have told earlier, we are going to find these four equivalent parameters in order to analyze a transistor. So we are going to find H11, H12, H21 or H22 or otherwise the Y terms or otherwise the Z terms. So we have three parameter models in order to analyze a transistor. The first one available is Z parameter model. The second model that is available is Y parameter model. And the third one that is available is called as a H parameter model. So why we are defining three different parameter model in sense, we are going to analyze a transistor using this Z parameter. Then what we will do is, we will do a open circuit operation in any one of the input or otherwise the output ports to get the this H11 parameters or Z parameters. So if at all we are going for the Y parameter, then we will use a short circuit operation in any one of the ports, namely a output port or the input port, to find the Y parameters, namely Y11, Y12, Y21 and Y22. So whereas if we are moving for this H parameter model, we will use both the open circuit as well as the short circuit model. So being this combines both Z and Y parameter, it is otherwise known as hybrid parameter. So we are going to use both the short circuit as well as the open circuit. We will do a short circuit here in order to find the input terms, that is VA or IA, and we will do an open circuit this side and we will find the I0 and V0 terms. So that is why it is called as hybrid parameter. So now we are going to use the hybrid parameter in order to model a small signal transistor. So from this two-port network, what we are going to do is, now we are going to write the dependency equation from this two-port network. So first we can write what are the inputs available, that is II and VI is the input available and I0 and the V0 are the outputs available. So first we can say, we all know that a transistor is a current control device. So we can say that II is a independent term. So we know that if IA is independent, then I0 is automatically a dependent term on the input current. So next comes the input voltage and the output voltage. Input voltage, if at all we want to get a 5 volt output, then we want to supply a 2 volt input. So this particular VI is dependent on the V0 and this V0 is independent of VI. So now we have 4 terms. Among these 4 terms, we have 2 dependent terms and 2 independent terms. We can write which are the terms are independent. For example, II and V0 is now independent terms, and we have the other 2 terms, that is VI and I0, which are dependent terms. So now what we are going to do is, we are going to frame the equations for this one. So first let us write, we have 2 different equations, that is independent one. First we can write it as II and V0 is independent. So we know 2 terms, that is dependent. The first one is VI. So we can write it as VI is in some factor, it is dependent on II and V0. So the second one is nothing but I0. So it is also in some factor dependent on II and V0. So we have a dependency between these terms. So now we are going to make these terms into a matrix format. From that matrix format, we are going to form the equation. So first we can write it in the form of a matrix. So first VI and I0 are the dependent terms. So next I am going to use a hybrid parameter model. So I am going to have H11, H12, H21 and H22. So next 2 terms which are independent are II and V0. So now we have a matrix. So from this matrix, what we want to do is, we want to form the 2 equations. From the 2 equations, we are going to draw the transistor equivalent circuit. So now what we are going to do is, we are going to write the equation from this matrix. So see here, it is a normal multiplication. So we can write it as VI, which is equal to H11 into II plus H12 into, so the another term is V0 here, and the next one is nothing but I naught equation. For this we have to write it as I naught is equal to H21 into II plus H22 into V naught. So now we have the two equations. From this equation only we are going to draw the small signal equivalent circuit for the transistor. So this is a basic equation. So we can name it as 1 and this equation as 2. Okay. So now what we have to do is we are going to find this values, that is H11, H21, H12 and H22 in order to replace it here to draw it into a circuit. So first we can take the first equation, that is VI is equal to H11 into II plus H12 into V naught. So as I have told earlier, what we did is we have to do a short circuit or a open circuit operation in order to get the H11 or H12 or H21 or H22 parameter values. So first, in order to get these two values, what I am going to do is, first thing I am going to apply a short circuit in the output. So normally we know that if we apply any short circuit operation, the voltage, that is the voltage what we have considered here is output voltage. So the voltage, that is V naught, will be equal to 0. So automatically the equation becomes VI is equal to H11 into II. So in the next step what we can do is VI divided by II. So this is the answer for H11. So now we can see a similarity. We know the formula V is equal to IR. So we know that R is equal to V divided by I. See here, these two equations are same. So we can say this one as a resistance. And we know that here we have a term called I. What it denotes in sense, it denotes that it is an input. So we are going to say this one as a input resistance. So being this is called as an input resistance, we can term this H11 as HR, that is not HR, it is HI. So being this is an input resistance, we are going to name it as HI, and the unit of resistance we all know that it is nothing but ohm. So now we have obtained the first equation H11, we have obtained the value of H11 and we have replaced that in terms of HI, and the unit of that HI is nothing but ohm. So now we have to find the next term. So in order to find the next term, we are going to use the same equation, which is nothing but VI is equal to H11 into II plus H12 into V naught. So first what we did is, we have did a short circuit operation in the output side. Now what we are going to do is, we are going to do a open circuit operation in the input side. So then automatically what happens is that, if we do a open circuit operation, the input current, that is II, will be equal to 0. So the equation becomes VI is equal to H12 into V naught. So that next step we will have the equation as VI divided by V naught, which is equal to H12. So now see, we have an input divided by the output. So it resembles that some amount of the output voltage is reflected back into the input. So we can term this as reverse transfer voltage. That is, some amount of the output voltage is transferred back into the input. So being this is a reverse transfer voltage, we can term this one as HR, and see here, in the numerator as well as in the denominator, we have both the terms as voltage. So what we are going to do is, there is no unit for this. Being both the terms are of same, that is voltage, we don't have any unit for this one. So next what we have to do is, we have to analyze the second equation. So the second equation is nothing but I naught is equal to H21 into II plus H22 into V naught. So from this equation we are going to find the H21 and H22 terms in order to make the equivalent circuit of a transistor. So similarly what we did in the first equation, we are going to do the same thing here also. So first thing is nothing but we are going to short the output. So V naught will be equal to 0. So the equation is I naught is equal to H21 into II. In the next step the equation will become I naught divided by II, which is equal to H21. So we all know that whenever there is any terms or ratio is available with output divided by input, then we can say that particular equation as a gain. So we have a current here, both the terms are in terms of current, so we can term this one as a current gain. So being this is called as a current gain, we can say that one as Hi. Okay. So the current travels in a forward direction, so we can call this one as Hf. So again we are replacing this one as Hf, and being this I naught and II is of same terms, we do not have unit for this. So we have derived the third parameter also. Now what we are going to do is, we are going to derive the fourth parameter, that is nothing but H22. So for that also we are going to use the same equation. So that is nothing but I naught is equal to H21 into II plus H22 into V naught. In order to find this H22 equation, what we have to do is, we are going to do a open circuit operation here. So what happens is I naught will be equal to 0. So automatically the equation becomes I naught is equal to H22 into V naught. So in the next step I naught divided by V naught, which is equal to H22. See this equation is a reciprocal of resistance, that is 1 by R. So normally we name it as admittance, and being here is a O which represents the output, we can say that one as a output admittance. So the particular term can be called as a H naught. Okay. So this is a reciprocal of resistance, and we know the unit for this as mho, which is a reciprocal of ohm. So now we have analyzed 4 terms, that is H11, H12 and H21. So first one is H11, the second one is H12, the third one is H21 and the fourth one is H22. So first one is H11, which is the input resistance, so it is represented as Hi, and the second one is H12, which is nothing but a reverse transfer voltage, so it is represented as HR, and the third one is H21, which is nothing but the forward current gain, and it is represented as Hf, and the fourth one is H22, which is nothing but the output admittance, which can be called as a H naught. So now we are going to replace the equation. So now we can replace the equation. We know that the first equation is nothing but Vi is equal to H11 into II plus H12 into V naught, and the second equation is nothing but I naught is equal to H21 into II plus H22 into V naught. So now what we are going to do is, we are going to replace the H11, H12 and H21 and H22. So first we can replace Vi is equal to Hi into II plus H12 is nothing but a reverse transfer voltage HR into V naught. The second equation becomes I naught is equal to H21 is nothing but the forward current, so we can replace this Hf and II plus this is H naught and V naught. So the equation 1 and 2 becomes like this, which can be named as 3 and 4. So from this equation, what we are going to do is, we are going to draw a equivalent circuit. So before drawing a equivalent circuit, let us have a simplification of this equation. So in order to simplify the equations, what we are going to do is, we are going to substitute the values of Hi and Hr. So first let me consider the first equation, that is Vi is equal to Hi into Ii plus Hr into V0. So now I know the values of Hi and Hr. So what I am going to do is, I am going to substitute the values of Hi and Hr. So now see, Vi is equal to, Hi is nothing but a Vi divided by Ii into Ii plus Hr. So the Hr term is nothing but I, that is V input divided by V0 into V0. Now can I cancel it out? Ii and Ia get cancelled, and here V0 and V0 get cancelled. So I will automatically get the equation as Vi is equal to Vi plus Vi. See this entire equation, this equation is entirely in the form of a voltage. So I can name it as a voltage equation, and I can draw an equivalent circuit for this particular equation using a Thevenin's equivalent circuit. Okay. So because this equation is full of voltage, we are going to draw it using a Thevenin circuit theory. So next we are going to analyze the second equation. So we know that the second equation is nothing but I0 is equal to Hf into Ii plus H0 into V0. So now what I am going to do is, I am going to substitute the value of Hf and the value of H0 in order to find the equation. So first I0 is equal to, the Hf is nothing but, it is a ratio of current. So it is I0 divided by Ii into Ii plus output admittance. So we can write it in the form of I0 divided by V0 into V0. So I can cancel the terms Ii and Ii and V0 and V0. So automatically I have the equation as I0 is equal to I0 plus I0. So this shows that this entire equation is in the form of a current, so that I can utilize a Norton circuit theory in order to draw the equivalent circuit for this particular equation. So now we have found the two equations for, that is voltage and for the current. So now what we are going to do is, we are going to draw the equivalent circuit for the Thevenin circuit theory and the Norton circuit theory. So let us draw the equivalent circuit model now. So from this equation only we are going to draw the equivalent circuit. So just for the simplification purpose I have showed you the Norton circuit theory and the Thevenin circuit theory. So I am going to use the 3 and 4th equation only. So first let me consider the first equation, which is nothing but Vi is equal to Hi into Ii plus Hr into V0. So let me consider Vi first. So it shows that we have provided some voltage, that is Vi as the input. So next what we have is Hi into Ia. So we know that Hi is nothing but the input resistance. So a resistance will be usually represented as in this form. So we can write this one as Hi. So and we have a current through this resistance, which is nothing but Ii, that is the input current. And after that what we have is Hr into V0, which is nothing but a voltage, and we are going to represent that in a form of a voltage generator. So why I have drawn this two parameters in a series instance, I am using a Thevenin's equivalent circuit. So if at all two voltages are added, then we have to draw it in a form of a series. So I have drawn this in the series form. So now I know this is HR into V naught. Okay. So now I have completed the first equation. Now I have to draw the equation for draw equivalent circuit for this second equation. So see what is the that is the output current I naught is available. Let me leave that, and after that I have HF into IA. We know that it is a forward current, so we can draw that as a generator of current. So next term is nothing but H naught into V naught. The H naught into V naught is nothing but the current. So we are going to represent that in a form of a resistance. Why? In sense it is a output admittance. So being that is a output admittance, it is a reciprocal of resistance. So we are going to represent that also in a form of a resistance. So now why I have drawn these two terms in parallel instance, I have utilized the Norton circuit theory for this particular equation. If I utilize a Norton circuit theory, I have to make it in a form of a parallel. When the two currents are added, then it has to be in a parallel. So I know this one is nothing but HF into II, that is the input current flows here. Here it is plus and minus, here it is also plus and minus. So this term is a reciprocal of resistance, so I can write that one as 1 by H naught, and after that I have a V naught which is nothing but the output voltage, so I can write it here as a V naught. So now I have drawn the equation for first equation and also for the second equation. So now I can connect it like this. So this is the equivalent circuit for the small signal transistor. Okay. So this we have obtained for the general equation. Now let us see how we are going to obtain the equation for the CBC and CC configurations. So we can consider a CE configuration. So first let me draw a basic diagram of a CE configuration transistor. So we know that for a CE configuration, emitter is common. So we can draw like this, and next, so the input will be applied between the base and the emitter. So from the collector we will have the output. So it is drawn like this. We will have the voltage between the base and the emitter as VB, and we will have the output voltage between the collector and the emitter as VC, and the input current will be represented as IB and the output current will be represented as IC. Now I know all the four terms which is going to determine this equation. So first let me write what are the inputs and what are the outputs. So first one is nothing but IB is the input current, and I know that the collector is the output. So it is the output current, and VB is nothing but the input voltage, and the fourth term is nothing but VC, which is the collector voltage, that is the output voltage. So being all these terms are for a CE configuration, now I am going to replace this equation. So now I can write this one as IBE and ICE and VBE and VCE. So I have just added E in order to make it clear that it belongs to the CE configuration. So now I am going to replace the IBE, ICE, VBE and VCE terms in the equation. So let me write the equation first, that is VI is equal to HI into that is nothing but the input current II plus HR into the output voltage, that is V naught. The second equation is I naught is equal to HF into I plus H naught into V naught. So now I am going to write the equations in the terms of CE configuration. So first I know that the input voltage is nothing but VB. So I can write it as VBE is equal to HI is the input resistance, and after that the input current is nothing but IB So, I am going to replace that as IBE plus I have HR. So, I can write it as HR, and after that I have the output voltage. I know that the output voltage is nothing but a VCE. So, I am going to represent this one as VCE, and the second equation is in terms of output current. So, I know that the output current is nothing but ICE. So, ICE will be equal to HF into II is nothing but the same, that is the base current, that is IBE, plus we have the H0 and V0. So, we have to represent it as H0, and the V0 is nothing but the output voltage, which is nothing but VCE. So, for this equation, now we are going to draw the simplified equivalent circuit now. So, we know that we are going to apply a VBE between the base and the emitter. So, we can draw it like this. So, next we have a resistance. So, for this we will term that one as HI, and we know that the input current is nothing but IBE. So, we are writing it as IBE, and after that we have the voltage generator. So, we have the HR into VCE, that is the output voltage is reflected back in the front side, and after that we have the second equation. We have the current generator here. So, which can be written as HF into the current that flows is IBE, and after that we have the H0 into VCE. It is a reciprocal of resistance. So, we are going to draw it in a form of a resistance, and we are going to write it as HO into the output voltage which we have provided as VCE. So, being this is a base emitter, that is a collector common emitter configuration, what we are going to do is, this is the input base and this is a collector, and the common term is nothing but E. So, we can term like this. So, this is about the small signal equivalent circuit for the transistor in the CE configuration. In a similar way, we can draw it for the CC and CB configuration. So, let us end up the session with this.